Hi. So we are in chapter 3, application of Boolean algebra. Also, the final frame here is related with combinational circuit. So in here we explained how we can set up a combination circuit by using the gates. Now we're going to show you how we can model this or analyze a combinational circuit. So let's go in details. So there are many examples here. Any combination circuit given to you means type of elements, which type of elements connected how is given to you. So analyze a combination circuit like that is to find out a truth table or to find a Boolean function representing this combination circuits. Here you are, just a few examples. Here it is just one output combination circuit. If you look at this one, the second one has got two output Boolean function. So if you compare the inputs, so this one has got 5 inputs. So if you want to make a truth table for this combination circuit, so you're going to have a 2 to the power 5, 32 rows and one output, just one output. So number of columns is going to be 6. For each variable, one column. So total 1 column for the function as well. So altogether 6 columns. For this one, for example, we've got 7 variables. 7 variables means 2 to the power 7 rows on the truth table. And we've got 7 plus 2 outputs, 9 columns to represent a truth table for a combination circuit like that. So these are big truth tables, aren't they? So by using this truth table, how you can get that truth table? For each row, you're going to use the definition relation of these elements and find out the output. So it is not an easy job to handle. So instead of this, what we are saying, we can write just one function, one Boolean function for each combination circuit. Then anytime we can calculate any row of the truth table from this Boolean function easily. So let's increase the examples here. If you look at this example here, it's got 4 inputs, 1 output. This one also has got 4 input and 1 output. And these two circuits does the same job. So different elements included, different connection, and you get same function. So in here we've got 3 AND gates, 1 OR gate. In here we've got 2 AND gates, 2 OR gates. So the number of element types changes. On the other hand, this is a 2-level realization and sum of product form realization. This one is mixed one and it has got 3 levels. From input to the output, you've got to pass 3 elements. So it is a 3-level realization, but they are equivalent. So in order to write this function, so output of this AND gate is x1 times x2. Output of this second AND gate is x2 times x3, that's second product term. And the last one is x3 times x4 is the last product term. Addition of those 3 with an OR gate gives you the output function f. So if you normally draw a truth table for analyzing such a circuit, you are going to have 16 lines, 16 rows, and 5 columns in order to represent the truth table for this function. So in here we've got only one function here, one line. How simple it is. So for any row in the truth table, the function value can be calculated by this formula. Let's say all of them, all the inputs are 0, so 0 times 0, this gives you 0, this gives you 0, this gives you, add them up, 0, so f function is 0. So I can calculate each row by using this Boolean function or this formula formatted Boolean function. So for this one now, function is going to be multiplication of those two and summation of those two times multiplied with x3. So this second one here is this line function. This product term is this line function. Summation of those two gives you the function. This function is exactly the same as this function, but although the functions are equivalent, the way of writing the formula for those two equivalent functions changes. If you look at this one, for example, this is just to give you an example saying that you can represent functions, representing functions might be in different formats. For example, for this one, it is sum of product form. This one, product of sum form, isn't it? So just one function represents this function, this combination circuit. Just one function represents this combination circuits as a conclusion. So this example is quite interesting. In here, the type of elements, all of them the same type. So you don't have to buy different type gates in order to set up a circuit like that. For example, this is one integrated circuit. You could do this realization. But for this one, you've got to use different integrated circuits, one of them, and the other one is OR. But in this case, they are all NAND, so just one. So we can write this function. So I left it to you to write this function. So this writing the function is the mathematical model of this combination circuit. So conclusion is any one input combinational circuit can mathematically be modeled by a Boolean function. Another way of saying it, for each output of a combination circuit, so you've got to write one Boolean function in order to analyze this circuit. So that is the end of this video then.